Okay, so we have started recording and all right, we are set now. So we have covered quite a bit of ground yesterday. Now there are a few things left. In the meantime, yesterday evening, I have also released the tutorial sheet 4. Now, unlike the previous tutorial sheets, this particular tutorial sheet, it contains quite a few questions which are like derivation based, and a couple of them are also posed in a way that you will just have to think about it and just write down the answer or just put forward your reasons for it. So there is nothing to derive or nothing to calculate in those two couple of questions. So I think that will trigger some proper intellectual exercises. Nevertheless, if you have any problems, you can ask them. I will try to point out certain things from that tutorial sheet. But before I can do that, I just want to mention a few points as a continuation of the previous discussions. So first of all, it has to do with the Mohr circle. So I had mentioned yesterday that the Mohr circle is a good visualization technique, and as far as the precise calculations are concerned, we actually nowadays use the formulas. We code them up and use them directly, those formulas for finding out the actual values of the transformed stresses. But still, many people, even if they don't directly keep on drawing the Mohr circle, they do use the Mohr circle as some kind of a sanity check. Sanity check means suppose they do some calculations, the Mohr circle can still give us some sort of a geometrical understanding of the overall situation. Okay, so it's like a cross check kind of thing. It's a good visualization thing. So in that sense, it has its certain usefulness. And in some of the problems in the tutorial sheet, I have asked you to solve problems taking up both the approaches. Furthermore, just like we are now considering most of for our discussions, the two-dimensional state of stress, which is referred to as the plane stress, where sigma zz equal to 0, tau zx equal to 0, tau yz equal to 0, it is possible to have obviously a three-dimensional state of stress, and corresponding to that, a three-dimensional version of the Mohr circle also. You don't have to go about drawing spheres for that. It's just that in place of one circle, you have to draw three circles. So in the tutorial sheet, there are some things that I have asked you to derive and see for yourself, which go beyond the stuff that is discussed in our textbook by Beer and Johnson. So I'll quickly mention one thing about the Mohr circle, which was asked near the end of yesterday's class. Like, suppose we do not rely on the formula, is there any way to draw this Mohr circle? Because if it is so that maybe 100 years ago, and I think Mohr circle was, kind of invented, so to speak, in the 1880s. So 140 years ago. So when people actually use the Mohr circle properly without the use of calculators or anything, how did they go about doing it? So it is kind of instructive to take a look at that. So it's something like this, that you have a stress element, suppose you have a stress element, or you have some information regarding the stress in this fashion, that let's say you know the value of sigma xx. Okay, you know this value. Let's say you know this value also, the sigma yy value, and you know this value, the tau xy value, which means that you know the tau yx value also. So all these things are known. Okay, so for this two-dimensional state of stress, all you need is these three independent pieces of information. Now with this, what we can do is we can draw these axes, sigma and tau, Now, as with almost everything else in mechanics and mechanics of solids, there are certain conventions to follow. They are not just arbitrary lines in the sand that older gentlemen have just, they've chosen to draw. It's not like that. There's a certain motivation behind it. So you see here, we want to depict first of all what is available to us. The available information is this sigma xx value, tau xy value, and the sigma yy value. So now on this sigma tau plane, how do we express that? If we can do that, it will give us a method to construct the Mohr circle and to go forward and try to obtain values of the transform stresses in other planes also. So first of all, for sigma xx tau xy, so considering this particular plane, this vertical plane on which you have the sigma xx and tau xy values. Let's say our sigma xx is here. Okay, so this is the point with the coordinate sigma xx0, but we are not interested in that. Okay, we are interested in sigma xx tau xy. Now, you will definitely now say that sigma xx tau xy, suppose if both of them have positive values. Let's say sigma xx is 20 megapascals and tau xy is 10 megapascals. So you will say that it will be something like this. It will be a point somewhere here. Okay, no problem there. But there is a problem in the sense that when you want to make a connection between the rotations on this sigma tau plane with the actual rotations that are taking place in this physical plane, because see, this is the geometrical sigma tau plane and this here is the actual physical plane. So if we want to make a connection between this plane or the rotations in this plane and the rotations in this plane, there will be a mismatch if you take that tau up in this first quadrant. Okay, so a convention is followed which keeps things very neat and organized. Convention is like this. So for every tau which has a tendency of rotating the stress element in the counterclockwise direction, okay, I repeat, for every shear stress that has a tendency of rotating the stress element in the counterclockwise direction, it is taken. So in the sigma tau plane, it is taken as a negative value. Okay, so counterclockwise is taken as negative in this sigma tau plane, and everything that is clockwise like this has a tendency of rotating the stress element clockwise, that is taken with a positive value in this sigma tau plane. Now, this is one of the reasons for which I am not particularly fond of the this is my personal feeling, okay, why I am personally not very fond of the Mohr circle business. Because you see, according to our earlier positivity convention, this tau xy, suppose it has a positive value, this is actually positive. And this direction is also positive by our positivity convention. But if you go by this convention, which is required for drawing the Mohr circle, this is the counterclockwise thing, because it has this tau xy has a tendency of rotating this stress element in the counterclockwise direction. This is supposed to be negative. Okay, so you're supposed to draw it in a negative fashion. And then this particular tau xy, which is also supposed to be, which is actually positive, but in the convention of the Mohr circle plane, you are supposed to take this as positive. Okay, but it is what it is. People have accepted it, people are using it, so we'll also have to use it. So suppose your tau xy has a positive value, you are supposed to take it down here. Okay, so this is with the understanding that if sigma xx is equal to, let's say, 20 MPa and tau xy is equal to 10 MPa, but this has a tendency of rotating the stress element in this direction, then it is down. But this one, so we say that this is, let's say, in the language of Beer and Johnson, this is the point X. And let's say this other point, this other thing, sigma yy tau yx combination, let's say that is something like sigma yy is, let's say, 5 MPa. And your tau x yx is also supposed to be equal to 10 MPa, because we know that these two magnitudes are the same, but this has a tendency of rotating the stress element in the clockwise sense. So it will be on the upper half. So 5 MPa is somewhere here. So it will be something like this. So this is your point y. So these two together, they constitute the point y, and these two constitute the point x. So maybe it will be better if I just choose something else, maybe a or something. Otherwise this x and y is very confusing. Although in Beer and Johnson they have used x and y. I'll use something else. This is B and this is A. This is all that is given to us from this stress element diagram. Now what you do is you join these two. So all this is done graphically now. You have selected or you have drawn these 2 points, and then you just join these two. When you join these two, it will cut this abscissa, this x axis at this point. So that will be the center. Now you know the center, you also have the radius. You take a compass, put the pointed end here, put your pencil here and draw the circle like this. So this is completely a graphical construction. There is no role of the calculator here, and please accept that this is a circle. Okay, so this is supposed to be the diameter of that. So this is your Mohr circle. That's it, finished. Okay, and with this with this diagram done, let me try to make it closer to a circle. It's much easier to draw a circle on a blackboard. Okay, so this is our circle, and then you can identify that this particular point, this will be denoting one of the principal stresses. This will be denoting one of the other principal stresses. Okay, and you can make a quick check. So it's something like this, that what is this angle? Okay, try to see what is this angle. So let's say this is O. So angle AOP1, tan of that. What is that? Tell me.
So tau x by y.
Tau x y. Okay, then
Sigma xx minus sigma average.
what?
So divided by sigma xx minus sigma average.
Can you tell me in terms of the coordinates of A and B? What you're saying is correct actually.
So sigma xx minus half of sigma xx plus sigma yy.
Yeah, but you're still saying in terms of A and O. I want you to say in terms of A and B. So A, the x coordinate is sigma xx. The B, the x coordinate is sigma yy. So it is simply half of sigma xx minus sigma yy. That's all there is to it. Okay. So, and this is we are speaking in terms of the magnitude. Okay, we are not talking about negative, positive, any trigonometric signs or all those things. I'm just taking this thing. Okay, so this much is tau xy, and this thing here, this is just the half of this thing. Okay, so I hope you are getting that. Okay, so this x coordinate is sigma xx, this x coordinate is sigma yy. So this is sigma xx minus sigma yy by 2. Now you check what is this angle with the previous things that we have. Can you just go back to your notes or maybe whatever you have? Can you check what is this thing?
So tan of 2 theta p.
Yes.
The principal angle.
Yes, yes. So this thing, if you go back and check, okay. You go back and check that this tan of angle AOP, that AOP1 that we have just drawn or that just written, that is nothing but equal to the tan 2 theta p that we had earlier found out, where this theta p denotes the orientation of the planes on which the principal stresses are occurring. And it makes sense. It makes sense. Why? Because you see this angle, it is the angle by which you have to traverse in order to reach this particular point. Okay, from here to here, when you go, you have to go by this angle. So this angle is required to reach this point, and this point is what? This is nothing but the principal stress point itself. Okay, so it is kind of consistent. Okay, now one important point which I want to highlight here is that had you taken this point not in this downwards, not in this bottom half, rather on the upper half, then the sense of rotation would have been clockwise. What I'm trying to say here is this, that earlier when we wanted to find out the plane on which the principal stresses were occurring, we took something like this. We took a plane like this, which was oriented to the x-axis by this angle. This was our theta p. So we were traversing in this counterclockwise direction. Now, when you are taking this point A downwards, it ensures that in this geometrical plane also you are making this kind of a journey in the counterclockwise sense. Had you taken it upwards, you would have to do it in the reverse sense. So the motivation behind taking this kind of a convention, okay, this counterclockwise, negative clockwise, is to actually ensure the consistency in the sense of rotation by which you have to change your orientation of the planes. Okay, both in this geometrical plane as well as in the physical plane. That is the only motivation here. Furthermore, you check one thing. Here, this angle is how much? This is AOP1, and that is equal to twice theta p. So in the physical plane, from this x-axis to this n hat, you have to go by theta p. But in this geometrical plane, you have to go by twice theta p. So a rotation in the actual physical plane by any angle theta is equivalent to an angle of rotation in the geometrical plane by an angle twice theta. Okay, and this is not just for the special case of the principal stress. Any two points or any two arbitrary orientations that you can think of, when they are tilted to each other by an angle theta in the actual physical plane of the stress element, in the corresponding geometrical plane, it corresponds to an angle of twice theta. And you can immediately check about this through this A and B point also. In the physical plane, this is the x-axis and this is the y-axis. They are tilted to each other by an angle of 90 degrees. All right, so the theta between them is 90 degrees. Okay, so this plane and this plane, they are tilted to each other by 90 degrees. But in this geometrical plane, this point OA represents the state of stress on this plane, and this point B, it represents the state of stress on this horizontal plane. And you see how much is the rotation from A to B. It is 180 degrees. So what was 90 degrees in the actual physical plane is 180 degrees in this geometrical plane. Always remember this. Okay, so these are the small sanity checks that you can carry out while doing your calculations. Okay, if your calculation is wrong, I mean, nothing will come out correctly. So, I mean, it's just a sort of cross check. Okay, so that's all there is to it regarding this Mohr circle. It is possible that you don't use your calculator, and for certain transformations, suppose someone asks you that, okay, you have this state of stress. What will be the state of stress if you rotate your stress element by 30 degrees? So all you have to do is go from this point A in the counterclockwise direction by 60 degrees, mark out a point there and determine the coordinates of that point geometrically. But that I believe, I mean, when you already have calculated, okay, no one does it nowadays, but you can do that. All right, this is one thing. Another thing is regarding the principal stresses. Okay, so we are slowly going into an area where although it appears that I am discussing theory, but actually I'm giving you hints for solving the problems in the tutorial sheet, and I will show you. So in the tutorial sheet, These are problems which are like two-dimensional cases only. All of these are two-dimensional cases, rather straightforward things. But you see, starting from here, I have started discussing some things, or I'm asking you to do some things associated with the three-dimensional things. Now, this question number 4 is pretty straightforward, but it's an important question. It's a very important question. Please do all of these things. But later on, you see, I have actually given you some problems. Okay, I've given you some problems involving the 3D state of stress. So all the components are there. I mean, some things are zero here, just to give you an idea about physical cases. But this question number 9A, that's a proper three-dimensional case. Nothing is zero here. You see, none of the components, okay, are zero here. Maybe sigma xz is zero, but in general, it's not zero. So I have asked you to determine the principal stresses as well as a bunch of other things. But the main thing is that once you have to determine the principal stresses. Once you do that, the other things just follow immediately. So for this principal stresses, well, you can do one thing, that this is just an eigenvalue problem, as I was telling you earlier. Okay, you can take a look at this thing also. This is an eigenvalue problem. You please note that in the two-dimensional case, proceeding from that eigenvalue problem only, we were able to determine the expressions of the unknown principal stresses, like the sigma p expressions. The only difference here is that instead of a 2x2 matrix, we have a 3x3 matrix. Now, there, in the two-dimensional case, we were considering these direction cosines of the unit outward normal to that plane, where the principal stresses would be occurring using cos theta and sin theta. But here you see it's a more general thing. These are actual direction cosines, nxp, nyp, and nzp. And you have to always remember that there is a connection which relates these three things together. What is that? What is the connection between the direction cosines? Who can tell me? You all know this. I'm just asking you. Yeah.
Sum of the squares equal to.
Yes, yes, yes. So you have already learned this in your vector maths earlier, maybe even in school. So nxp square plus nyp square plus nzp square, they are equal to, that's equal to 1. That's the constraint. Now, I believe in your your maths course, this MA11004, you have learned how to find out eigenvalues, right?
Yes, sir.
Yes, sir.
For both 2x2 and 3x3 matrices?
Yes, sir.
Okay. Now you don't have to do that much hard work. Okay. If you want, you can just check that you have not forgotten how to do those things. But in practice, nobody does all those things by hand, because there are, bigger and better things to do within the context of solid mechanics. If you keep on investing your time in doing those basic type of calculations, you won't be actually finding the time to appreciate the things which are important. So I suggest that for just finding out the values of the answers to the eigenvalues, the eigenvectors, all these things, you use directly the built-in functionalities present within Python or MATLAB. Okay, very straightforward. I'll demonstrate to you in just a second. Okay, so what I'm saying to you is this: when you come to this problem, if you want, just check for maybe one problem if you can still do those calculations of eigenvalues and eigenvectors by hand. But more importantly, note it. You please try to see how you can do it in Python and MATLAB. Okay, because both of them have built-in functions. Like MATLAB is very easy. Like, you just have to write EIG and just give the matrix. It will give you the eigenvalues and the eigenvectors. Python, you have to type in a couple of extra words, but it's again a one-line business. So this is the code. Okay, this is basically the thing. So see here, I've just defined this thing like this, a general matrix. So the stress matrix is like this. This is the first row, 125 minus 50, 0. This is the second row. This is the third row. And this is the heart and soul of this script. Okay, E values and E vectors, you can call them rabbit and tiger, doesn't matter. Okay, I have just named them as E values and E vectors just to know that the first output from this program, from this built-in program, is the eigenvalues, and the second one is the eigenvectors. So within this NumPy package, you have a linear algebra as a sub package, and within that sub package, you have this built-in functionality called EIG. In MATLAB also, it's called EIG, and you just have to provide this stress matrix, and lo and behold, it gives you the answers. That's it. As easy as that. Okay, so I suggest all of you to do these things. And if you try to solve these problems from the tutorial sheet using Python or MATLAB, it will really help you later on when you have to solve the problems from the assignments, from the tests in a time-bound fashion. Okay, so just before the day of the test, if you try to see, no, I have to save time, let me prepare a script in Python or something, at that time it will be too late. You will make some error in syntax, not something or the other will go wrong. At this time, you have sufficient time. Durga Puja holidays are also coming up. So utilize this time to pick up this basic syntax of writing these things and getting the answers in 1 second or 2 seconds. Okay, and once you have this thing ready, you can actually, make it behave as you want it to behave. Okay, I have just written the basic code here. You can make it even more, user friendly. Okay, you don't even have to write like this. You can maybe just write sigma xx equal to something, sigma yy equal to something, and tau xy equal to something. Directly put on the values, and then Python will just do the hard work and just produce the output for you. So there's a lot you can do here. Okay. Does anyone want to ask something regarding this? If not, let me continue discussing the other things which I wanted to discuss. Okay. Next is, you see, yesterday we were discussing the maximum value of the shear stress, right? So let me go back here. This maximum magnitude of the tau x dash y dash is r. That's what we had mentioned. And we had also figured out what is the orientation of that maximum value of the, on which plane the maximum value of this tau x dash y dash, or the maximum value of the shear stress, will occur. Okay, so just like we had found out the orientation for the principal stresses, we also found out the orientation for the maximum shear stress. And we have found out that they were at an angle of 45 degrees to each other, those two planes. Now, all that is fine in the very restrictive two-dimensional situation. Okay, and the important thing to note here is that this tau x dash y dash that you are finding out, this thing that you are finding out, this is actually not the absolute maximum. Okay, this is only the maximum in plane shear stress. This is very, very important to note. Maximum in plane shear stress. Which plane? The plane which you are considering. Okay, so if you are drawing a stress element like this, there are this sigma xx, the sigma xy, the sigma yy, all these things. So this plane of the screen, or the plane of the paper that we're working on, that is the plane we are considering. On that plane, the maximum shear stress is this, but it does not automatically guarantee that the absolute value of the maximum shear stress for a given situation will be equal to this in plane shear stress maximum. Okay, why that is so? Because every problem is three-dimensional. Okay, our world is three-dimensional. That means that when you are drawing a stress element like this, actually it is something like this. So when you are drawing a stress element in the form of a square, like this, what you are actually drawing is something like this. A very thin element. Remember that we were considering plane stress cases. This is the thin element. And if you are drawing things like sigma xx here, tau xy here, tau yx here, and sigma yy here, that actually means that you are drawing things like sigma yy here, tau yx here, tau xy here, and sigma xx here. You note here that on that plane, okay, perpendicular to the z-axis, your sigma zz is 0, tau xz is 0, tau yz is 0. But then, if you consider this entire three-dimensional problem, it may so happen that the maximum value, okay, so in general, the let me write that better, the absolute maximum value of the shear stress for a particular problem will be different, will not be equal to the maximum in plane shear in general. Okay, it can be, it is possible that the maximum in plane shear is itself the absolute maximum value of the shear stress, but in general the absolute maximum value of the shear stress will not be equal to the maximum in plane shear stress. Okay, and we had seen that the value was, the maximum value was the shear stress, in plane shear stress was R. Now, what was this R in terms of the principal stresses? Okay, so a quick question. Okay, I will not go back to that slide because if I show that slide, everyone will answer. You tell me, okay, in terms of the principal stresses, what is the let me write this maximum in plane shear stress we have already said that that is equal to R. My question is, in terms of the principal stress values, what is this R?
Modulus of principal stress minus average stress.
No, you can't involve the average stress. You have to tell me the answer purely in terms of the principal stress values. So for the two-dimensional problem, there will be two values of the principal stresses, sigma P1 and sigma P2. You tell me the answer in terms of sigma P1 and sigma P2.
Sigma P2 minus sigma P1 by 2.
Yes, absolute value of that, okay. So sigma P1 minus sigma P2 by 2. Now let me reveal to you why this is so. Let's go back to the Mohr circle. You see here it is sigma P1. Here it is sigma P2. This entire thing is the diameter, that is twice R. So twice R is equal to sigma P1 minus sigma P2. That is why R is equal to sigma P1 minus sigma P2. So remember this. So R is equal to sigma P1 minus sigma P2. And because R cannot be a negative quantity, and this is it, I mean, for this particular diagram, it's fine that sigma P1 is greater than sigma P2, but in general, we just write it like this so that it is ensured that this is an absolute, I mean, it's a positive value. Okay, now this is for the one dimension or the two-dimensional stress case. Now, if you go back to your tutorial sheet, you will see something that I have asked you to do. You look at this problem number 10. Okay, please do not get daunted or get afraid by all these things. Ultimately, the actual brain work that you will have to do is in this step. Okay, going from here to here, this is just algebraic manipulation. Okay, even a class 8 or 9 student will be able to do it. Your actual brain work is involves here. Okay, and even this is very, very straightforward. Now, the conclusions from that is very, very interesting. You see, just like earlier, we were able to obtain an equation of a circle from the transformation equations of the stress in the two-dimensional case. Here also we are obtaining certain equations, but there is a very important difference between the earlier case and this case. That important difference is not just in the number of equations that you have to deal with, rather it is in the sense of this thing. Okay, earlier it was an equal to. Okay, if you go back if you go back to the earlier slides that we were discussing, the first mention of let me go back as early as possible, maybe somewhere here. Okay, let me check which slide it was on. Right, so this is the part where I had mentioned that this is in the form of a circle. Okay, you see, this was x minus sigma average square plus y square is equal to r square. So it obtained this thing. Important thing was that this was an equality. So we were actually talking about points which are lying on the circle, on this thing. But now, when we are talking about the three-dimensional state of stress, we are not talking about an equality. Rather, we are talking about three inequalities. The implication of this is that when we are talking about the three-dimensional state of stress, what you really obtain is something like this. You actually obtain, and let me draw this thing properly. You obtain three circles. Okay, so those three equations, they represent, they are three inequalities. So each of them, had this been sorry, this is very bad. So this is the second circle, and then you'll have a third circle also. All their radii will, in general, will be different. Something like that. Okay, now if you just check here, and let me just take this thing to that. Okay, let me put this side by side. So this thing, okay, please check with this. Right, this is what I wanted. So you check with these things. You see there are three circles. They are representing, these inequalities are actually representing areas which are within the circle and outside the circle. You also note that these equations of the circles, okay, they are written in terms of the principal stresses. These sigma P1, sigma P2 and sigma P3, they are the three principal stresses. Now what we do is, in order to make our life a little bit easier and organized, we mark out or we arrange the principal stresses in this decreasing order. Okay, without any loss of generality, we can do that. So we say that this point here, this is sigma P1, this is sigma P2, and this is sigma P3. And just like the plan is here that we have to arrange them in decreasing order, you see they are in decreasing order. Sigma P1 is the highest value, sigma P2 is the intermediate value, and sigma P3 is the lowest value. Okay. Now you consider this circle, sigma TNN minus sigma P2 plus sigma P3 by 2. So this is the center of this circle. This is the x component of the center. So which circle is this corresponding to? So let me mark out these things. So this is C1, this is C2, and this is C3. You tell me which one does this equation correspond to? Which circle in this diagram does this equation correspond to?
C1.
Yes. So this corresponds, the first one, it corresponds to C1. Why? Because the center here is sigma P2 plus sigma P3 by 2. You see, this is sigma P2. This is sigma P3. So the coordinate of this thing is sigma P2 plus sigma P3 by 2. Okay, and of course the radius of this C1 circle is sigma P2 minus sigma P3 by 2, which is here on the right hand side. What is the second equation corresponding to? Which circle?
Circle C2.
Circle C2, right here. And you see, although I have not, there is no direct point here, but you'll see that this is involving sigma P1 and sigma P3. So this is sigma P1, this is sigma P3. It will be somewhere here. The center will be somewhere here. And the radius of that circle is this thing, sigma P3. Actually, this, I should have written this as sigma P1 minus sigma P3 by 2, because sigma P1 is larger than sigma P3, but there's a square here, so it doesn't matter. So you know that radius, okay? And the final thing, this C3 circle will be corresponding to this sigma P1, sigma P2. So involving this one and this one. All right. Now, after these things, and using the knowledge which you already have from, okay, using the knowledge that you have regarding the in-plane shear stresses like this, you tell me what is the maximum shear stress corresponding to this circle? What is the maximum in-plane shear stress corresponding to this circle? Forget about these equations now.
Sigma P3 by 2.
Please say that again.
So sigma P2 minus sigma P3 by 2.
Sigma,
that is the radius of
yes. Sigma P2 minus sigma P3 by 2. And this time we don't even have to put the modulus, because you have already chosen to take this sigma P1 greater than sigma P2 greater than sigma P3. Okay, so for the circle C1, this is the maximum in-plane shear stress. For the circle C2, similarly, you tell me what is it?
Sigma P1 minus sigma P3 by 2.
Very good. And finally, for C3, it will be just sigma P1 minus sigma P2 by 2. Now, among all these three, you tell me which is the maximum value.
The radius of circle C2.
Yes. So sigma P1 minus sigma P3 by 2 will be the maximum because of this thing, because sigma P1 is greater than sigma P2 is greater than sigma P3. So the highest difference between the or the difference between the highest value and the lowest value, that will give me the maximum of all these three different values. Individually considering the planes of this 1 and 3 and this 2 and 3, this 1 and 3 and this 1 and 2, they are the individual maximum in-plane shear stresses. But considering all of them, this is the highest value. Okay. Now, the thing that I want you to go back to is this thing. Okay, this diagram again. You see, here we have found out that there was some sigma P1 and sigma P2, and imagine that sigma P1 is greater than sigma P2. Okay, so we don't even have to use this absolute value. We have this thing as the maximum in-plane shear stress. Now you tell me, do you think in this case also, in light of the newfound knowledge you have regarding the 3D Mohr circles, do you think this is going to be the absolute maximum value of the shear stress or something else?
It may or may not be, depending upon the.
No. There is no depending. You're supposed to know the answer here.
So we
Think about.
consider relation between sigma P1, P2 and P3 in the decreasing order.
Yeah,
So
that's the thing. That's the thing. There is something hidden here, but hidden right in front of your eyes. What is sigma P3 here?
it's 0.
Why?
We are considering the plane, the stresses in a plane.
No, that is not the reason. Reason is very subtle actually. You see, we are claiming that is a very subtle thing, but a very nice logic. Okay, you don't even have to do any calculations. You see that we are saying that sigma zz is equal to 0, tau zx is equal to 0, and tau yz is equal to 0. Is it not? Now, according to the definition of the principal stresses, what are the principal stresses? The principal stresses are the normal stress components of the tractions on those planes on which the shear components of the stresses are 0. I repeat, the principal stresses or the principal stress on a particular plane will be such will be on such a plane on which the shear stress components are 0. Now you see on this particular plane, on this plane perpendicular to the z-axis, you do have sigma zx equal to 0, as this tau zx equal to 0 and tau yz equal to 0. So they are actually telling you that the shear stress components are 0. Because the shear stress components are 0, the value of the normal stress, that itself is the principal stress. So sigma zz is actually the sigma P3. It just so happens that sigma P3 is equal to 0. This is the reason. Okay. So now that you know that sigma P1 is some value, sigma P2 is some value, and sigma P3 is some value. Okay. And let's say that sigma P1, okay, say sigma P1 is greater than sigma P2 is greater than 0. And now you also have that uh, and we found that sigma P3 is equal to 0. Now you tell me what is the value of the maximum or the maximum absolute value of the shear stress.
Sigma P1 by.
Yeah, tell.
So sigma P1 by 2.
Yes. So therefore, maximum, like the overall maximum value, okay? So overall maximum value of shear stress is equal to half of sigma P1 minus sigma P3, and this sigma P3 is equal to 0. So this is equal to half of sigma P1. What will be the other value of the maximum in-plane shear stress that we have not talked about till now? One of them we have talked about is this, just the one that we have found out, half of sigma P1. One we have already talked about, which is this radius r, corresponding to the plane which is parallel to the xy plane. What is the third one that we have not talked about?
Sigma 2 by 2.
Yes, the third maximum in-plane shear stress will be that sigma P2 minus sigma P3 by 2, that is basically half of sigma P2. Okay, so you have three different choices of the maximum in-plane shear stress. Out of that, this is the absolute maximum value. Okay, so in many of the problems, you will be asked to specify the overall maximum value of the shear stress. So please do not write directly without thinking the value of the maximum in-plane shear stress. That will be completely wrong. Okay, take into consideration the overall actual three-dimensional situation and then write the answer. These are the kind of pitfalls which are very commonly given in examinations like GATE, IES, and so Indian Engineering Services, and certainly these are the kind of things which are very commonly asked during our comprehensive vivas also. Okay, comprehensive vivas are the kind of grand vivas which you have in your fourth year. But I don't know, maybe in your syllabus it is, in your curriculum maybe it has been done away with. I don't remember. But somewhere or the other you will have to face a viva. So These are the kind of things which are definitely going to be asked. Okay, so today we have not done any derivations, we have not done any calculations, but the kind of things that I have just discussed with you, they are of tremendous importance. Okay, whether you do theory or experiment or something, they are of tremendous importance. I cannot stress enough. Okay, so this particular tutorial sheet, it may not be as involved in a calculation wise as the other tutorial sheets, but please take this tutorial sheet very seriously. It's almost uh, like a ramp up in your brain level. Okay, so when you play video games or something, you have to, I mean, go from 0 level to 1 level to 5th level, then God mode or something like that. So this is a definite ramp up in your level. Okay, once you do this tutorial sheet, you'll have learned a lot in solid mechanics. Okay, so please do it very seriously. You can see in some of these answers I've actually asked the tau makes max absolute value, and then in the first problem I did not ask anything like that. I only asked about the maximum in plane thing. Okay, so there is a significant difference between these things. I have a couple of minutes left. You please read this question. It's a slightly tricky question, but it's not difficult, but slightly tricky question. You see, can you figure out how to solve this problem? Question number 3. So determine the principal planes and the principal stresses for the state of plane stress resulting from the superposition of the two states of stress shown. So you have one state of stress like this and another state of stress where the stress element is some kind of arbitrarily oriented. Please note that this black dot that is present here, that is the same black dot. So in one case you have the same state of this one kind of state of stress appearing around this black dot, and in another case you have this particular kind of thing appearing around the black dot. So when you superimpose those two things, what is the resulting state of stress? How do you do it to this problem?
So sigma xx will be 75 megapascal plus 50 megapascal times the the component of 50 megapascal in that direction.
You're talking about this 50 megapascal, right?
Yes, sir. Yes, sir. That will be that components will be taken in x and y direction with respect to the.
Right. But when you do that thing, you have to be a little bit careful in the sense that this is a certain state of stress. Okay, this is a certain state of stress, and when you do this problem, think of it like this, that the stress element is oriented like this and the other stress element is oriented very nicely like this, normal kind of orientation. From this one, you try to convert it to this one, this kind of an orientation. Okay, which means that all the states of stress, what you're doing, so your x-axis is like this. You try to rotate your x-axis in the clockwise direction like this, so that you are obtaining finally this kind of an orientation. Because once you obtain the stresses corresponding to this kind of an orientation, then this like that dotted orientation and this right hand side orientation, they are same to same. And then you can directly add up whatever the stresses are appearing on this vertical face and whatever the stresses are appearing on this horizontal face with these vertical and these horizontal faces respectively. Okay, that is the trick. In general, you can have many kinds of this superposition business, like you can have one stress element like this, another stress element like that. Somewhat can't seem to draw a proper square. Something like that. Okay, different orientations are there, and please note that these are all squares. So maybe this is at 30 degrees, this is at 45 degrees. Okay, so the best thing to do is to transform all of them to these kinds of nice orientations where this edge is actually vertical, this edge is actually vertical, and so on and so forth. So you can actually add them all up together. And the same kind of idea will be useful while solving this this problem also, this second one. Okay, It may look a little bit tricky, this one, but ultimately it's just a case of stress transformation properly. Okay.
Sir, you mentioned rotation in case of question number 3 for the first diagram.
Yeah.
So, do we also need to apply the transformation of stress formula for the 50 megapascal shear stress into corresponding sigma xx and tau values?
Before I continue, I'm noticing the clock. It is over. Okay, this period is over, so everyone is free to leave and go to the next class. So everyone, please leave. But those who want to ask a question may hang around. Okay. All right. So you were saying this 50 megapascal that has to be transformed.
Yes, sir. So you said we need to rotate it. So we need to geometrically just rotate it, or we need to transform the stresses also.
Transform. Geometrically only rotate and then you don't transform. What kind of business is that? When you rotate it, you have to transform everything properly. Otherwise, I mean, you're just tilting the computer. That is equivalent to that. No, if you're just saying that, no, I'll just rotate it by like whatever 60 degrees or something, that won't do anything.
Okay, sir.
When you rotate a stress element, correspondingly you have to use the stress transformation equations to obtain the stresses that would appear on those vertical edges after rotation, vertical and horizontal edges after rotation. Otherwise, you are just rotating your computer.
Okay, sir.
Yeah.
Sir, and one more thing, can the Mohr circle be on the two sides of y-axis?
Of course.
If there is excessive stress at some point.
Yeah, why not? Why not? So suppose your sigma P1 is positive and sigma P2 is negative, then only you will see, na?
Yes, sir.
It can be so that sigma P1 is equal to 10 megapascals, sigma P2 equal to minus 5 megapascal. So it will be asymmetrically oriented about the y-axis or the tau axis. It can be so that sigma P1 is equal to minus of sigma P2, in which case the center of the circle will be at the origin of the sigma tau plane. That can also happen.
Okay, sir.
Yeah. All right, guys, thank you very much.
Thank you, sir.